Welcome back, space enthusiasts. Today we're diving straight into an explainer that decodes the massive structure, the sheer scale, and the invisible secrets of our very own home galaxy, the Milky Way. We're going to piece together the exact clues that scientists use to map a colossal structure that, honestly, we can never actually step outside of. It's a giant cosmic detective story, and by the end of this, I promise you'll look up at the night sky in a completely different way. Let's get into it.
Section 1. The View from Inside. A cosmic detective story. Because that's exactly what this is, trying to map a house we can't ever leave.
Just grounding ourselves for a second with this absolutely stunning view from Mauna Kea, you can clearly see that familiar, cloudy band of the Milky Way stretching right across the sky. And, as you seasoned stargazers probably know, that band is simply our inside-out perspective of a vast, flat disk of stars. Basically, when we look directly at that band, we are looking through the absolute thickest part of the disk. Look away from it, you're staring straight out into the empty void of intergalactic space.
But right away, this brings us to a pretty massive fundamental problem. How exactly do we map a galaxy that we are physically trapped inside of? Think about it. Trying to map our galaxy is literally like trying to map a huge, dense forest while you're stuck sitting directly behind a massive tree. We can't just launch a probe high up above the Milky Way to snap a quick picture for us. We are embedded right in the thick of it, and worse, our view is incredibly obstructed.
So here's how we get around that. This brilliantly illustrates our biggest hurdle, interstellar dust, and the amazing technological solution we use to beat it. In standard visible light, these dark, shadowy patches of dust effectively blind us. They totally hide the galaxy's core. But switch over to infrared light, it's like putting on X-ray glasses. We pierce right through that dust. Infrared light just isn't absorbed in the same way, which affords us this spectacular, completely unobstructed view of the entire central structure of the Milky Way. It's a total game changer.
Moving on to Section 2, Anatomy of Our Galaxy, breaking down the pinwheel.
I love this classic lyric because it perfectly captures the staggering, almost unimaginable scale we're dealing with here. Really, let these numbers sink in for a second. We're talking about 100 billion stars. The whole structure? 100,000 light years side to side. To put that into perspective, if you were traveling at the absolute speed of light, which is roughly 186,000 miles per second, mind you, it would still take you 100 millennia just across it. It bulges at the middle, about 16,000 light years thick, but out by us in our neck of the woods, it thins out to just 3,000 light years wide.
So, mapping this out edge-on, we can basically break the Milky Way down into three main parts: the bulge, the disk, and the halo. And you are here! Our solar system is definitely not downtown in that super bright, chaotic central bulge. Nope, we are way out in the galactic suburbs. We're roughly 28,000 light years away from the center, just living comfortably out here in the flat disk of the galaxy.
But, the disk and the bulge are really only part of the story. Enveloping that whole shebang is the halo. Now, to be absolutely clear, this halo isn't just a bunch of empty space. Not at all. It's a bustling, massive, spherical envelope where these incredibly dense swarms of stars, known as globular clusters, orbit the galactic center. Think of these clusters as ancient, packed cities of stars just hovering high above and below the main galactic plane.
Section 3. 2 generations of stars. Galactic demographics.
Now, what's really fascinating about mapping our galaxy is finding out that its residents are clearly divided into two distinct demographics: Population 1 and Population 2. Population 1 stars, they're the younger generation, found right in the disk. They are rich in solar metals, and they move in neat, orderly circular orbits. Population 2 stars, on the other hand, are the elders. They reside out in the bulge and the halo. They can be up to 12 billion years old. They are super metal poor, and they have these highly random, almost chaotic orbits.
And tracking this demographic data is exactly what helps us perfectly reconstruct the Milky Way's history. Over the course of 10 to 12 billion years, these different generations of stars formed, burned out, and died, enriching the galaxy's stock of heavy elements along the way. But actually, here's the craziest twist. Before this organized disk even formed, the future Milky Way very likely existed as several distinct ancient galaxies that fell together and violently merged. We are literally living in the remixed remnants of a massive cosmic merger.
Section 4. The dark matter mystery. The twist in the spin.
Okay, so just when we think we have the geography and the demographics of our galaxy perfectly mapped out, we have to look at how this entire massive structure actually spins. In a planetary system, like our own solar system, objects that are farther away from the center orbit much more slowly. For example, Neptune just kind of plods along way slower than Mercury. Astronomers naturally expected our galaxy to behave exactly the same way. But when they measured the galactic rotation curves, they found something shocking. The stars way out at the outer edges of the galaxy don't slow down at all. They maintain incredibly high orbital speeds, way faster than the visible gravity should even allow.
So why does this matter? Well, this rotational anomaly tells astronomers something profound. It means our visible pinwheel of stars and gas is actually turning inside an enormous, spherical cloud of completely invisible matter. The visible mass, those 100 billion stars we just talked about, simply cannot explain those high-speed orbits at the edge of the galaxy. Without this unseen mass acting as a sort of gravitational glue, the Milky Way wouldn't just be spinning fast, it would literally fly apart. We call this invisible phantom mass dark matter.
Section 5. Our universe's ultimate fate. Beyond the Milky Way.
Solving the immediate physical layout of the Milky Way was an absolutely incredible feat of science. But as astronomers took additional measurements, they realized this wasn't just some localized quirk of our own galaxy. No way. These measurements regarding invisible mass cracked open an even larger, mind-bending puzzle. This dark matter isn't just holding the Milky Way together. It actually seems to be the dominant form of mass across the entire observable universe.
Which brings us to the ultimate question. I want you to really ponder this. If this invisible, untouchable matter is the true puppet master that's holding our galactic home together, what does that mean for the ultimate fate of the entire universe? Does this massive amount of unseen mass have enough gravity to eventually pull the universe back in on itself? Or is it just going to keep expanding forever? It's a lot to think about. Keep looking up, keep asking those big questions, and I'll see you in the next explainer.